So far, we have treated characteristic roots as real numbers. For the linear ODEs with real coefficients that we are considering, characteristic roots can also be complex. When they are complex, they come in conjugate pairs. We can write the pair as A equals sigma plus minus j omega. The reason for the conjugate pair is that the original ODE has real coefficients. That means the characteristic equation also has real coefficients. If we multiply the two corresponding factors together, A minus sigma plus j omega times A minus sigma minus j omega, the imaginary parts cancel. This gives A minus sigma squared plus omega squared. If we expand this, we get A squared minus 2 sigma A plus sigma squared plus omega squared, which is a real polynomial factor in the characteristic equation. The roots are still the values of A. The real part is sigma and the imaginary part is omega. In this video, we will see that the real part affects growth or decay of the response, while the imaginary part gives oscillation. The complex root pair A equals sigma plus minus j omega gives exponential solution terms of the form e to the power of sigma plus minus j omega times t. Using the exponential rule, we can split this into e to the sigma t times e to the plus minus j omega t. Euler's formula tells us that e to the power of plus minus j omega t is cos omega t plus minus j sine omega t. The j sine omega t term does not mean the real valued response is imaginary. Because complex roots come in conjugate pairs, the conjugate exponential terms are taken together. Adding them gives the cosine part, and taking their difference gives the sine part. This is why the final real valued response involves sine and cosine terms. Now, let's focus on the real part, sigma. In the response term, e to the sigma t multiplies the oscillation. This multiplication factor sets the envelope. It determines whether the oscillation gets smaller, stays the same size, or gets larger. If sigma is less than 0, the envelope decays, so the oscillation gets smaller over time. If sigma equals 0, the envelope is constant, so the oscillation is sustained. An ideal undamped oscillator, such as simple harmonic motion, is one example of this case. If sigma is larger than 0, the envelope grows, so the oscillation gets larger over time. The previous three cases describe non-repeated complex roots. There is one extra case worth separating: repeated purely imaginary roots. Because these roots are repeated, the repeated root idea introduces powers of time. For example, we can get terms like t cos omega t and t sine omega t. That means the oscillation is not growing exponentially, but its amplitude still grows over time. This is an example of algebraically growing oscillations. If roots are repeated more times, higher powers of time can appear. But the example shown here gives linear algebraic growth. The imaginary part of the complex root is omega, and omega tells us how fast the oscillation occurs. To understand what omega means, we need to connect three related quantities. Angular frequency, omega, is measured in radians per second. Frequency, f, is measured in cycles per second. Period t is the time for one complete cycle. The link between radians and cycles is that one full cycle corresponds to 2 pi radians. So, Angular frequency and frequency are related by omega equals 2 pi f. And because frequency is 1 over the period, f equals 1 on t. Combining those gives omega equals 2 pi on t. This figure shows a simple oscillation. X of t equals sine omega t, plotted over time. The amplitude is 1, so the oscillation varies between positive 1 and negative 1. One full cycle takes 2 seconds, so the period is t equals 2 seconds. That means the frequency is f equals 1 on t, which is 0.5 cycles per second. Since one full cycle is 2 pi radians, half a cycle per second corresponds to pi radians per second. So, in this example, omega equals pi radians per second. That means the oscillation moves through half a cycle every second, or equivalently, pi radians every second. More generally, larger omega means the oscillation moves through its cycles faster. Visually, the cycles get squeezed closer together in time, which means the period t becomes smaller. To connect this back to stability, we use the solution terms to describe how deviations from equilibrium behave over time. If the real part of A is less than 0, the oscillation decays, so the deviation goes to 0. This corresponds to asymptotic stability. If the real part of A is equal to 0, the oscillation is sustained. The deviation remains bounded and does not go to 0. So this corresponds to marginal stability. If the real part is bigger than 0, the oscillations grow. So the deviation moves away from the equilibrium. This corresponds to instability. There is one extra case, a repeated root with the real part of A equals 0. In that case, the powers of time can multiply the response terms, so the response can grow algebraically. This corresponds to algebraically unstable behavior. The imaginary part gives the oscillation frequency. In other words, the imaginary part of A equals omega tells us how fast the oscillation occurs. So, the real part tells us whether deviations decay, remain bounded, or grow, while the imaginary part tells us how fast they oscillate.